Good afternoon, everyone. So today in this session, we'll be starting with a new chapter that is thermodynamics, right? So in the last previous chapter, we discussed about the ideal gas and ideal gas equations, right? And here we'll be studying the thermodynamics of the ideal gas here, right, in this chapter. So this chapter of the thermodynamics will be purely based on the thermodynamics of the ideal gases, right? So let's begin with the first important term, that's the thermodynamic system, right? Thermodynamic system. So what is actually a thermodynamic system, right? So actually thermodynamic system is a portion, or we can say it's a part of the universe, right? Which actually is under study, right? Which is under observation. And that part of universe which is under observation or that are under study, right? Let's suppose we study for a certain portion of the universe. We're studying the pressure, we're studying the volume, we're studying the temperature for a specified portion of the universe, right? Then we call that as a system, right? So the system which can be represented in the form of pressure, volume, and temperature, that's what we call as the thermodynamic system, right? Or we can say a part of universe which is under observation, right? Or we can say that the part of universe which is actually under study, which is studied, right? And its volume is studied, its pressure is studied, its temperature is studied. All these thermodynamic variables are studied, right? Then that part of the universe we call as system, thermodynamic system, right? So, and these physical quantities, the pressure, volume, temperature, these are called as thermodynamic variables, right? These are the thermodynamic variable, right? So let's suppose, for example, we are gas enclosed in a cylinder, right? And it's fitted with a piston, right? Let's suppose we have this container, right? This is the container. This is the container, right? And in this container, we have a gas, right? In this container, we have a gas. This container is filled with some gas, right? Let's suppose this container is filled with the oxygen gas, or we can say nitrogen gas, any gas, right? It's filled with. Now there's a piston, right? It's fitted with piston on the top, right? It's fitted with the piston on the top. Now you can see here, this gas will have certain pressure, right? And the volume occupied by this gas will be the volume of this container, right? And this gas will also have certain temperature, right? So these three physical quantities, pressure, volume, and temperature, we call as thermodynamic variables, right? Thermodynamic variables, because we can change all the three physical quantities of a particular thermodynamic system, right? Now you can see here. Now, if we supply some heat energy externally, let's suppose Q amount of heat is supplied to this Q amount of heat is supplied to this gas, right? Or we can say to this system, right? So what we can see that, let's suppose if it's a movable piston, right? If it is a movable piston, then what's going to happen then? Thermal energy of this gas molecules will increase, right? There is a possibility that the piston of this container will move up, right? Or it will slide up, right? The temperature of the system will increase, right? The temperature of the system will increase. When the piston moves up, definitely the volume occupied, now there is more volume or more space available for the gas uh, to be in, right? So the volume of the system actually increases, right? The pressure will change, right? So all these observations taken for this part of the universe, which is under observation, where we study the pressure, we study the change in pressure, volume, temperature, right? Or we can say we study all these thermodynamic parameters or thermodynamic variables, right? So that part of the universe which is under observation, and observation is done with respect to these physical quantities or these thermodynamic variables, right, for a system. And that system we call as thermodynamical system, right? We call that as a thermodynamical system, right? So this is a very fundamental concept, right? Thermodynamical system, right? Then we have the surroundings, right? We have the surroundings, right? So surroundings, anything left apart from the system, we call it as surrounding, right? So, or we can say surrounding is the part of the universe, right, apart from the system, right, with which a system can exchange the heat energy, with which the system can exchange the matter, right? And which tends to change actually the properties of the system. That's what we call as its surrounding, right? Now let's suppose the system and the surroundings together will make the universe, right? That's the thermodynamic term for the universe, right? Now you can see here, uh, there is a container, right? There's a container, and this container is fitted with a piston, right? This is a piston here, right? It's fitted with a piston, and this piston can be a movable piston, right? Now you can see here there's a part of this system which actually separates surroundings with the system. That's what we call as boundary, right? That's what we call as boundary. Now we are studying in this container the part which is actually observation is the gas filled in this container, or gas in this chamber, right? Gas molecules in this chamber. So this part of this universe we will call it as system, right? Now the gas, some particular gas is a system for us because we are studying this particular gas. This particular gas is under observation. We are studying its pressure, we are studying its volume, we are studying its temperature. So all these thermodynamic variables are studied, right? Are under observation. So this will be a system for us, right? Then there is a piston, and surrounding plus the system together make a universe, right? These are the some basic terms, right? Now let's talk about the let's talk about types of systems, right? We are talking about the types of systems. Now, systems can be of many types, right? Depending upon the interaction of the system with the surroundings, right? Depending upon the interaction of the system with the surroundings, we have some certain types of the systems, right? The first type of system we call as open system, right? It's an open system, right? It means that there will be a direct interaction between the system and the surrounding. Let's suppose we have this container, right? We have this container, and it's an open system, right? In this container filled with gas. This container is filled with gas. This container is filled with gas, right? Now in this container, this container is filled with gas. We will call it as open system, right? Because for this system, there is a direct interaction between the system and the surrounding. The exchange of the matter can take place. The exchange of the heat energy can take place, right? So the exchange of matter can take place. Exchange of heat energy can take place, right? So such systems are called as open systems, right? The systems where both the exchange of the matter as well as uh, the heat will take place. Exchange of the matter as well as heat will take place between the system and the surroundings. Such systems we call as open systems, right? Then we have a closed system, right? Let's suppose if we close this system with a piston on it, and this piston is a immovable piston, right? This piston does not move, right? Even if we increase the temperature of the system, right, the pressure of the system will increase, right? But the piston of the system will not move, or we can say there is no direct interaction, right, between the system and the surrounding, right? So, matter exchange of matter between the system and the surrounding is not possible in case of the closed systems. Only there is a possibility of exchange of heat energy between the system and the surroundings, and such systems we call as closed systems, right? Closed systems, right? So such systems are called as closed systems. So in case of closed system, we have majorly three types of the system. One is open system, another is closed system, and the third one is isolated system. So in open system, there is a direct interaction between the system and the surroundings. So in open system, both matter and the exchange of the matter as well as heat energy can take place, right? So that system we call as open system, right? Now let's suppose we have a cup of a coffee, right? If we have a cup of a coffee, right? Then we will call it as open system, because we know that if we place a cup of a coffee, right, then the heat exchange will also take place, as well as the interaction. There will be direct interaction between the system and the surrounding. Exchange of the matter will also take place. So apart from the exchange of the matter between the system and the surrounding, the exchange of the heat energy also takes place, right? So such systems we call as open systems, right? Then we have closed system. Only the interaction, heat energy exchange will take place, or there will be no direct interaction between the system and surrounding, or we can say that exchange of the matter is not possible between the system and the surroundings in case of closed system, right? Then we have the third system. That's the uh, what we call as isolated systems, right? Isolated systems, right? So in case of isolated systems, right? So isolated systems are actually closed systems, right? Closed systems where the exchange of the heat energy exchange of the heat energy is not possible between the system and the surrounding, right? Right. We can write no exchange of energy, right? No exchange of energy between system and the surrounding. So in case of isolated system, there will be no interaction between the system and the surrounding. There will be no exchange of the matter between system and the surrounding, and there will be no exchange of the heat energy between system and the surrounding, right? So such systems we call as isolated systems, right? So these are the three types of systems we have with respect to the depending upon the interaction of the system with the surroundings, right? Now let's discuss about the thermodynamic state, right? The thermodynamic state is nothing. Let's suppose we have a container, right? We have a container, and in this container we have kept some gas, right? We have kept some gas in this container, right? In this container, there's a container, right? And in this container we have kept some gas, right? It's filled with gas, and this container is filled with gas, right? Now, if you want to know the pressure, right? Pressure, volume, and temperature of the system, right? If we want to know pressure, we can measure the pressure of the system. We can measure the volume of the system. We can measure the temperature of the system, right? So here, by thermodynamic state, we mean that what are the we need at least two thermodynamic variables to define the state of a system, right? Either in case of ideal gases, right? Either we know the pressure and the volume, right? If we know the pressure and the volume, then we can know the temperature about the system, right? If we know the volume, pressure and temperature, then we can know about the volume of the system, right? Or we can, if we know the volume and temperature of the system, right, we can know about the pressure of the system, right? So these are the three thermodynamics variables, right, which actually define the state of a system, right? State of a system. So by state of a system, we mean that what is the pressure or the temperature of the system, right? Or what is the pressure or the volume of the system, or what is the volume or temperature of the system at the in a given conditions, right? So that's what do we mean by the thermodynamic state, right? So these are the three thermodynamic variables which are very important to define the thermodynamic state, right? Then we have the thermodynamic process, right? Then thermodynamic process is nothing. These are actually the path followed to change the thermodynamic state from one state to another state, right? Or the successive paths followed, right? The successive paths followed to change the thermodynamic state from one initial state to some final state. That's what we call as the thermodynamic processes, right? So in these processes, we may change the pressure, we may change the volume, we may change the temperature, right? Uh, so all these steps, or we can say all these successive states through which system passes, that's what we call as to arrive at the final thermodynamic state. That's what we call as the thermodynamic process, right? Now let's suppose we have a gas in this. You can see in this diagram we have a gas at A, right? This is the thermodynamic state at A, right? In this graph, right? You can see here we are reaching we reach the state B through different processes, right? You can see here initially what we do is that we increase the pressure of this gas, right? And the pressure becomes maximum, then we decrease the pressure of this gas, it becomes minimum, then once again we increase the pressure of this gas, right? Then once again we decrease the pressure of this gas. Volume continuously increase for this particular gas, right? You can see from left to right the volume is continuously increasing, but there is a at sometimes there's an increase in the pressure, and then suddenly there's a decrease in the pressure, and then once again there's an increase in the pressure, right? So these successive states through which the system passes, right? Or we can say all these successive states through which the thermodynamic variables actually change, right? Such successive states through which this system goes, right? We call this as a thermodynamic process, right? So in thermodynamic process, the state of the system, thermodynamic system changes, right? From one state to another state through different paths, right? So that's what we call as thermodynamic process, right? So you can see here also we can go through different paths from one state to another state, right? It means that to achieve the same final thermodynamic state, we can follow different successive states, right? Or we can say we can follow through different thermodynamic processes to achieve this final thermodynamic state, right? So that's what how we actually understand by the thermodynamic process, right? So pressure, volume, and temperature are the important thermodynamic variables to change the state of a particular thermodynamic system, right? Now let's discuss about the work done by the thermodynamic system, right? Now let's suppose that here in this case we have this we have where the container, and at the top of this container there's a piston, right? It's a movable piston, right? Let's suppose the area of this piston is A, and let's at this instant, let's suppose the pressure of this gas is P, right? Pressure of this gas is P, and there must be definitely some force on this piston that will be given by pressure multiplied by the area, right? So this much of force will be applied. This much of force will be applied on this piston, right? It's a movable piston, right? It can slide up, right? It can slide up, and we know that whenever any force displaces a body, right? Displaces a body, then we say the work has been done, right? In the same manner, this gas filled in this chamber, right? Gas filled in this container can actually move this piston up, right? It can move this piston up, or it can slide this piston towards the right, right? Because of the force, because of the pressure inside this container, right? So there will be some work done by this gas, or we can say there will be work done by the system, right? Because the gas present in the container is the system for us, right? So the work will be done by the system, because this system will slide this piston through some displacement. Let's suppose dx displacement, right? Dx is the displacement through which this piston slides, and it is because of this pressure in the gas, right? Pressure in this container, right? Now you can see here, we know that any work done of the work done dw will be defined as, it is nothing, it's integral of f dot dx, right? If it's along one of the coordinates, right? Along one of the axes, right? So integral of f dot dx will be the total work done, right, by any force, right? Now you can see here, we can replace this force by pressure multiplied by area, right? Pressure multiplied by area, right? And since it's along the direction of the force, displacement is along the direction of the force, so we can write here f dx, right? F dx, right? So their dot product will be f dot dx will be f dx, right? So here we can replace this force by pressure multiplied by area, right? Pressure multiplied by area. That will be pressure multiplied by area, and we have this a length, or we have this displacement dx in the horizontal direction towards right. Now area multiplied by, now you can see here the volume of this system must have increased, must increase, right? Let's suppose initially there was some V1 volume, right? There will be some TV a change in the volume, right? TV change in the volume, right? That's the change in volume, right? Once this gas displaces the pistons towards the right. Now you can see here in this diagram, this much will be the volume that will be changed for this thermodynamic system, right? Now this volume will be nothing. It has to be equal to area multiplied by the displacement, right? So area multiplied by displacement must be the change in volume, right? So we can replace here area multiplied by the displacement by the change in volume. That's TW will be equal to integral of PdV, right? Integral of PdV, right? So that will be the total work done, right? That will be the total work done, right? So total work done delta W will be given by integration of this pressure with respect to this volume, right? Let's suppose initial volume was V1, and after some displacement dx, there is volume V2. So we can integrate it between the limits V1 to V2. Then definitely we will get the work done by the system, right? Work done by the system. Now you can see here, uh, the gas here is expanding. The gas will only, the system or the piston will expand, or the gas will expand only when the force on the piston is along the direction of the displacement, right? Or the piston displaces along the direction of the force, then in that case work done has to be a positive, right? Work done has to be a positive, or we can say that the expansion is only possible when work is done by the system, right? The expansion is possible when the work is done by the gas in the system, or we can say during expansion work is done by the system, or work is done by the gas present in the system, or we can say the work done by the system is taken to be positive, right? The work done by the system has to be a positive work done, right? It will be a positive work done if it is done by the system, right? done by the system, or we can say if there is expansion, or if there is an expansion. And similarly, let's suppose the same some force is applied by the external agents, right, on the piston of this system, right? Then definitely the piston is going to slide towards left, right? It will be you can say that you can see that the work done will be done on the system, right? Work will be done on the system. Then the change in volume will be a negative change in the volume, or in that case, we say that the work is done on the system, or we can say we take that work as the negative work, right? So work done on the system is taken as negative, and the work done by the system is taken as positive, right? Because for positive work, the change in volume will be positive, and for the work which is done on the system, the change in volume will be a negative change in volume, right? That's the reason we take the work done by the system as positive and work done on the system as negative, right? So these are the two conventions which will be followed for the work done in thermodynamic systems, right? Now we can see here the integral of PdV is nothing. We can write it as we can interpret it as between V1 to V2. It's nothing. It's area under pressure volume graph, right? Area under pressure or PV graph, right? Area under PV graph. So area under PV graph is nothing. It will give us the work done, right? It will give us the work done. So area under pressure and volume graph will give us the work done. That's area under PV graph. So area under PV graph will give us the total work done between the volumes V initial and V final, right? So thermodynamic processes, right? One by one. Let's suppose here in the first case, here in this diagram, you can see here there is some constant pressure here, right? And the volume is increasing for the system, right? There's a PV diagram, right? It's a constant, right? Constant graph parallel to the volume axis, right? You can see here there is definitely some work done by the system, right? Because here the expansion takes place, right? You can see here the volume is increasing, the expansion has taken place, right? Expansion has taken place, or we can say the work done by the system is actually a positive work here, right? I can see here the total work done. There is some pressure P here. The total work done will be given by the area under this PV graph. So the area under of this area under this PV graph will be nothing. It will be it's a rectangle here, right? So it will be a pressure, right? Delta V, that will be height multiplied by the base of this rectangle, right? The height of this rectangle is, let's suppose, pressure P, and that base will be given by the change in volume. That will be delta V, right? That will be V final minus V initial. So here you can see this work is a positive work, right? It's a positive work. And similarly here, the compression takes place, right? Now here in this case, it's a volume versus pressure graph, right? Here volume is a constant, right? Volume is constant, right? Volume is constant, or we can say the change in volume here is zero, right? If the change in here volume is zero, the work then has to be equal to zero, right? There will be no work done on the system, neither the work will be done by the system, right? Now here in this case, there's a compression. It's a volume versus pressure graph. You can see here the compression has taken place, right? Because the volume has decreased from A to B. So in this case, compression has taken place, right? Or we can say delta V will be a negative, right? That there will be negative change in the volume, right? So compression has taken place, right? If the compression has taken place, right? Then the volume has decreased, right? Then the work done has to be negative work done, right? So it means that the work done can be positive, negative, zero, right? So if expansion takes place, the work done will be positive. If compression takes place, the work done will be negative. And if uh, volume does not change, then the work done will be zero, right? Now we'll discuss different types of work in different work done in different thermodynamic systems, right? We'll be discussing the work done in different thermodynamic systems. Now let's discuss the work done for different thermodynamic systems. Let's begin with the isobaric process, right? Let's discuss this process. That's what we call as isobaric process, right? Isobaric process, right? So isobaric process is nothing. It's a thermodynamic process where the pressure of a system remains a constant, right? The pressure of the system remains constant. So let's suppose this is the pressure versus volume graph, right? This is the PV diagram, right? Pressure versus volume diagram, pressure versus volume graph. Now, in this case, what's going to happen is that the pressure will remain constant, right? Pressure will remain constant and the volume will change. That will be from V1 to V2, right? V1 to V2. So isobaric process, nothing. The pressure of the thermodynamic system remains constant, right? Pressure is constant. So such system we call as isobaric system, right? Pressure is constant. So if the pressure is constant here in this case, we know that when the pressure is constant, the volume is proportional to the temperature. If the volume increases, right? If the volume increases, the temperature has to increase, right? Now you can see here the work done will be nothing. It will be area under this curve, right? It will be area under this curve, right? This will be the work done. Or we can find this work done W. It will be integral of PdV, right? PdV, right? PdV. Now pressure is a constant. We'll take it outside this integral. The volume changes from V1 to V2, right? So it will be equal to P V final. That's V2 minus V1, right? That will be P delta V, right? P delta V. That will be the work done, right? So in case of isobaric process, right? In case of isobaric process, the work done is given by P dV, right? Or P delta V, right? That's the work done, right? Now, we know using the ideal gas equation for an ideal gas, PV is actually equal to nR uh, T, right? PV is actually equal to nRT, right? So if we differentiate on both sides, right? If we take the differentiation on both sides, right? It will be PdP, right? Plus VdP plus PdV, right? PdV. That will be equal to nRDT, right? nRDT. It will be nRDT, right? Now you can see here in this case the pressure is a constant, so dP has to be equal to 0, or we can say we can replace PdV as nRDT, right? nRDT. So it means that in case of isobaric process, we can replace PdV with nRDT, right? So the work then can be also calculated as it will be nRDT with the limits of the temperature T1 to T2, right? That will be equal to nR delta T, right? nR delta T. So either the work done for isobaric process, we can find it using P delta V or nR delta T, right? So it will be nR T final minus T initial, right? T final minus T initial. So it means that both the work done are equal actually, right? So P delta will V has to be equal to nR delta T. That will be equal to nR T final minus T initial. So this is how we can find the work done for a isobaric process, right? This is how we can find the work done for an isobaric process, right? So for isobaric process, the work done is simply nR delta T, or if we have been given a pressure versus volume graph, it will be a straight line, right? Parallel to the volume axis, right? And the area under this rectangle will be given, will give us the total work done, right? The area under this rectangle will give us a total work done. Let's suppose the constant pressure is P naught, then we will calculate the area, right? So from here to here, it will be P naught, right? And the base here will be V2 minus V1. The area of this rectangular portion here will be nothing. That will be P naught V2 minus V1, right? V2 minus V1. This will also give us the work done. And in this case, it will be a positive work done, right? It will be a positive work done, right? So this is how we find the work done for a isobaric process. So for isobaric process, the work done is P delta V or R delta T, right? Now let's move on to the next process, right? Let's discuss the isothermal process, right? So in case of isothermal process, we know that the temperature remains constant for a system, right? T remains constant. Temperature remains constant. Temperature remains constant for an isothermal system, right? Temperature remains constant. If we draw the PV diagram, right, we know that according to Boyle's law, if the temperature of the system is constant, then the pressure versus volume graph will be a rectangular hyperbola, right? It will be like this. So it will be a rectangular hyperbola, right? Now you can see the pressure, if we increase or decrease the pressure, then the volume will be increasing, right? Now the area of this pressure versus volume graph will give us the work done, right? Work done between the volumes V1 and V2, right? So this area will give us the work done. Since the expansion is taking place, the work done will be a positive work done, right? It will be a positive work done, right? Now calculating the work done in isothermal process, right? We'll be using the same equation, that's integral of PdV, right? We know for ideal gas, P is equal to nRT upon V, right? nRT upon V, right? So temperature is a constant. We can replace uh, P with nRT upon V dV, right? With the limits, let's suppose between V1 and V2, right? The work done here will be nRT is a constant. It will take it outside. So integral of dV upon V with limits V1 to V2, right? It will be equal to nRT. The integral of dV upon V will be nothing. It will be log of V, right? The limits V1 to V2, right? So the total work done will be nRT ln V2 upon V1, right? V2 upon V1. So this will be the total work done in case of isothermal process, right? In case of isothermal process, right? Similarly, if we have to write in terms of pressure, right? In terms of pressure, we know that PV is a constant, right? It means that P is a constant in case of isothermal process, right? So if PV is a constant, then P1 V1 has to be equal to P2 V2, right? Then we can replace V2 upon V1 will be equal to P1 upon P2, right? So we can write it in terms of pressure as well, right? So it will be equal to, the work done will be equal to nRT ln P1 upon P2, right? P1 upon P2. So this will be the work done in terms of pressure for isothermal process and the work done in terms of volume, right? So this will be the net volume, net work done in case of isothermal process, right? Now talking about the next process, that's the isochoric process, right? Isochoric process. In case of isochoric process, the volume remains constant, right? The volume remains constant. Volume is a constant, right? Volume of thermodynamic system is constant, right? If the volume of a thermodynamic system is constant, then the change in volume has to be equal to zero, right? Then work done has to be equal to zero, right? Or we can say in isochoric process, there is no work done at all, right? Because there is no expansion or no compression for the system, right? And the work done will be equal to zero. So it will be a straight line parallel to the pressure axis, right? That will be the graph for the isochoric process, right? So in case of I, you can see under this line, there is no actually area covered, right? No area covered under this line. So work done has to be equal to zero. Change in volume here is equal to zero, right? So let's discuss the final process work done by the adiabatic process, right? Work done in case of adiabatic process. So adiabatic process is a process in which there is no exchange of the heat energy between the system and the surrounding, or we can say dq is equal to zero, right? The heat exchange between the system and surrounding is zero, right? So such process we call as adiabatic process, and these processes are the quick processes, right? There is actually a very short time between short time, right? Actually, it has to be a quick process so that there is no net exchange of heat between the system and the surroundings, right? Such process we call as adiabatic process, right? Now, talking about the work done or the equation of the state for the adiabatic process, that's PV upon gamma is a constant, right? PV upon gamma is a constant, where gamma is nothing. It's a, we call it as adiabatic exponent, right? Adiabatic exponent, or is the ratio of the heat, specific heat capacities at constant pressure and constant volume, right? That's given as Cp upon Cv, right? That's equal to gamma, right? So that's what we call as the gamma, right? So gamma is different for different gases, right? Depending upon the uh, atomicity of the gases, right? Whether it's a monatomic gas, whether it's a diatomic or triatomic gas. So for different gases, the value of gamma is different. We'll be discussing that later, right? So for let's discuss calculate the work done because of this adiabatic process, right? So PV to the power gamma is a constant here, right? It means that we can replace here PV to the power gamma. We can replace it with constant K here. Let's suppose K is the constant here, right? We have to calculate the work done because of this because of this adiabatic process, right? We'll be using the same equation that the total work done W will be equal to integral of PdV, right? Integral of PdV, right? We can replace this pressure with K upon V to the power gamma, right? K upon V to the power gamma. So we can integrate it K upon V to the power gamma with respect to volume, right? Let's suppose we are integrating it between the volumes V1 and V2, right? K is a constant. We'll take it outside for integral of V to the power minus gamma dV, right? With limits V1 to V2. Now, the integration of V to the power minus gamma will be V to the power minus gamma plus 1 upon 1 minus gamma, right? So it will be V to the power minus gamma plus 1 upon 1 minus gamma. So this will be the integration for this V to the power minus gamma with the limits V1 to V2, right? Now we can take this 1 minus gamma outside. It will be K upon 1 minus gamma, right? With the limits V2 and V1, we can write here it as V to the power 1 minus gamma, right? V to the power 1 minus gamma minus V1 to the power 1 minus gamma, right? So that will be the work done. Now, where to calculate this constant K? We know that PV to the power gamma is a constant, right? If PV, P1, V1, P1, V1, PV to power gamma is a constant, then we can replace this uh, we can replace this K with either P1 V1 to the power gamma, right? So in this case, P1 V1 to the power gamma has to be equal to P2 V2 to the power gamma, right? It will be equal to, once again, this constant K. We can replace this constant K P1 V1 to the power gamma, right? So W will be equal to P1 V1 to the power gamma upon 1 minus gamma, right? Right? V to the power 1 minus gamma, right? Minus V1 to the power 1 minus gamma, right? And now multiplying, so we have P1 here, right? We have the value P1 V1 to the power gamma. We'll write it like this: P1 V1 to the power gamma upon 1 minus gamma, right? V to the power 1 minus gamma, right? Minus gamma minus V1 to the power 1 minus gamma. Right? Now W here will be P1 upon 1 minus gamma, right? V1 gamma V2 power 1 minus gamma, right? Minus, now here V1 gamma multiplied by V1 1 minus gamma, so bases are same, powers will be added, right? It will be nothing, it will be equal to P1, right? It will be equal to V1 to the power 1, right? It will be equal to V1 to the power V1 to the power gamma, V1 to the power 1 minus gamma, right? Now you can see here P1 V1 to the power gamma, V2 to the power 1 minus gamma, right? Minus, the base of same powers will be added, right? It will be V1 to the power gamma minus gamma, right? Plus 1, right? That will be divided by 1 minus gamma. Now this will be cancelled, right? This will get cancelled. So W will be equal to P1 upon 1 minus gamma, right? P1 to the power gamma, V to the power 1 minus gamma minus P1, right? Now here in this case, you can see you can replace this. You can once again use this equation P1 to the power P1 V1 gamma is equal to P2 V2 gamma, right? So once again, we can manipulate this work done as well, or we can use the ideal gas equation as well. That's PV is equal to nRT. We can write this work done in terms of temperature as well, right? We can write this work done in terms of temperature as well. So the basic equation, fundamental equation to calculate the work done through for any thermodynamics process is P integral of PdV, right? That's integral of PdV to calculate the work done for the different thermodynamic processes, right? So that's it with respect to the work done calculation for different thermodynamic process, right? Be it isochoric, adiabatic, isothermal, and isobaric process, right? In the next lecture, we'll be starting with the first of the thermodynamics, right? And we'll be discussing some of the questions as well, right? So let's stop here. See you in the next lecture.